Hi, welcome to lecture 6.2. So today we're going to talk about finding volumes of solids using integrals. We're going to talk about volumes by slicing. We're going to talk about volumes of solids of revolution and another multiple methods to do volumes of solids of revolution. So we'll see what all those mean pretty soon. Last time we talked generally about the idea of finding total things by adding up small things. One thing we could do was total area by adding up vertical slices, line segments. And for volumes, we're going to do this kind of thing, adding up slices, sort of 2D slices, to get the whole thing. So, the first method we're going to do is sort of directly doing this slicing thing, and then the next two are slightly more exotic. So let's try this one first. So we're going to use an integral to find the volume of a solid that's built of specific slices. So my picture before pretty much gave you the idea, but let's look at this GeoGebra example. So here we have, there's two functions. The red function is a function, I think it's square root of x, and the blue function is x squared. And what I'm going to imagine, this is going to be a little hard to picture, which is why I'm trying to show this, is slices which are squares. So I'm only drawing one slice here, but I'm imagining a full 3D volume which is built out of these slices in such a way that, if I move the slices along, different slices can have different sizes. So I imagine that I have like something that's vaguely, like potato shaped-ish, and when I cut into my potato, I get this slice, horizontal slice, which happens to be a square. So, so I imagine like literally like chopping a vegetable, and I look at the side, and the slice happens to be a square shape. At the skinny end, the slices will be small squares. In the middle, there'll be the big squares, and then at the other end, there'll be small squares again. We could imagine different volumes that have different cross sections. So instead of a square, I might have an equilateral triangle cross section. So again, I still have my potato that I'm slicing. It just turns out that when I look at it from the side, the slices are triangles. And again, the triangles will change size as you go towards the ends. You could imagine any shape. So we could have semicircles. Now this is really starting to look a bit more like a potato, maybe. Maybe you cut it in half already, right? So that you only have half the potato. And then when you slice them, you're going to get these semicircles. And again, you can move, they'll be smaller towards the ends, etc. So it's kind of hard to picture the whole thing at once. Often when we work on paper, we're going to really just be drawing this. So I'm going to be drawing pictures like this, where I just draw this one vertical line, right? And that's actually is going to turn out to be enough information to answer the problem, which is why it's useful just to draw that. But that's always going to be like a shortcut for imagining, oh, if I turned that sideways, there'd be this piece sort of sitting out of the page. So there's a semicircle like attached to the page, where its base is this vertical line that I'm drawing. That would be true if I had a different shape, right? Maybe a square. I just draw this vertical line, but it's actually the base of a square that is sticking out of the page, perpendicular to the page. You'll notice that if I have different shapes, right, my drawing looks the same. This kind of top-down drawing looks the same. So the problem will always tell you that, hey, maybe I draw this picture, but the cross-sections are squares in this problem. Or maybe in this problem, they're, actually equilateral triangles, right? The reason we just need the line, right, is that basically what we're going to be adding up is the areas of each of these slices, these vertical slices. So what's the area of this slice? Well, it's a square, right? The area changes as you go along. It's smallest when the two functions are close together, and it's big when the functions are far away from each other. And specifically, right, the area of a square is the base times the height. And because the square, the base and height are the same. So it's the base times the base, whatever that number is. Whatever this base length is, that number squared. So the base squared. What's the base squared? Well, what's the base? Come back up here. The base is just this distance, right? From the top function to the bottom function. And that's just like we did in last lecture. I take the top function and I could subtract the bottom function. No matter where the square is positioned, this top function minus bottom function as a formula will tell me the length of that line segment. And then I'm just going to square that formula in order to get the area of that square. I'm going to integrate all the way through. Integrate from where to where, right? From the beginning over here to the end over there. And so I'm going to have to do algebra like last time, solving for those intersection points. If we had like a semicircle instead, for example, then it's pretty much the same story, right? What's the area of a semicircle? Well, I'll have to remember my area of a circle is pi r squared. So the radius of this semicircle is the main piece of data I need in order to find the area. How do I connect the radius of this semicircle to the graph? Well, the radius is like half the diameter, right? The diameter is the total distance from one end of the base to the other, and half of it is the radius. So I really just have to find the diameter. And the diameter is just this top minus bottom, right? This line segment again. So I'm going to take my diameter, which is top minus bottom. I'll cut it in half to get the radius, and then that'll be the radius that I do pi r squared to get the area. Pi r squared over 2, actually. So don't worry, we'll write all this down, but I'm just trying to give you like an idea of how you can think about it just by kind of looking at it, and hopefully it makes some sense. Again, if we had a different shape, again, the main data I need is this base segment. I can get that by subtracting the functions, and then I'll use that to find the area of this triangle. Notice that it's actually important here that we use these specific shapes where, like, to get the area of the square, I only needed one side length, right? If I told you the cross sections are rectangles, that would not be enough information because I don't know how tall the rectangles are. The square is constrained where the height is the same as the base, so it's enough for me to just tell you that it's a square. That's enough. But, you know, the problem could say the slices are rectangles with width, with 2 or something like that. And then the height would still change depending on the function, but the width would be the same all the time, or something like that. So yeah, for a square and a semicircle, it's completely determined by the length. The area is determined by the length of the segment, and that's also actually true for an equilateral triangle, right? The area just depends on the length. And we'll actually do some algebra, or you can do algebra to determine that function exactly. Okay, before we head back to the paper, I do want to show off what this might look like if you actually have the entire volume. So here we only have one square, but I can imagine having another square. So there's 2 of them, right? And I can move it from left to right, and we can see kind of in more detail sort of what the total volume would be. If I add in some more squares, there's 9 of them now. Now you're starting to get a sense, maybe, of what the overall volume is. So it's showing a bunch of cross sections sort of all at once. And if I just pump this up to lots and lots and lots and lots and lots and lots of squares, so that's basically doing the integral, right? We're kind of pretending to go to infinity squares. So if I pull this all the way to the right, that's going to get me all the way to the end. And my overall shape, my volume, is this thing. Whatever you want to call this. Not really a potato, I guess. It's more of a, I don't know, like a leech or something. But yeah, it's kind of a non-trivial shape, right? Like if someone just handed you this shape and they were like, hey, you do some geometry to find the volume of this shape, probably have no idea, right? It's not like a standard geometry shape. It's kind of weird. there's no, in fact, the only way I know of to find an area of a shape like this, like mathematically, is, or the volume of the shape, is to do an integral like this. Yeah, and if if you encountered a shape like this in the wild, whatever that means, and we're trying to find its volume, if you wanted to use calculus on it, the idea would be, I guess, convince yourself that, oh, this is in fact made of slices, and then use the formulas we're gonna see. Yeah, it's possible your shape the slices could change like what they are partway through also, and that's kind of suddenly way more complicated. Here, we can use integrals and it's pretty powerful, but it is going to be sort of restricted to situations where I know it's exactly like the slices happen to exactly be squares. Let's just see what it would look like also to do this with the other shapes real quick. So if I do equilateral triangles, here's a couple, and then here's a bunch. So we get some sort of fish sort of shape maybe. Notice how the top curve like sort of bends as you go, which is sort of interesting. I think it's because like the top and bottom functions are not totally symmetric, so like at the beginning it's pulling the center point more towards the top function, but that sort of changes as you go through. So yeah, so we get this sort of shape, and let's just look at the semicircles. This is probably the most half a potato of them all. You can kind of see, yeah, sort of a nice shape. But these are, again, the slices are all semicircles. Okay, so yeah, it's really good just to have these pictures in mind as you're doing these problems. That's what we're doing, and just really try to remember a great way to think about the problems is to draw what I'm going to draw, which is a single slice, and sort of look at it from the top down and think about that's the line segment that I need to know in order to find the area. Okay, so let's come back to the paper. So we're going to define the volume of that region we just saw with square or with semicircle cross sections. So that last one we saw. Find the volume of solid with base, the region bounded by these curves whose cross sections are semicircles. So this is how the problems will often be phrased. Just make sure the language makes sense. Solid with base, the region bounded by. That's kind of a mouthful, right? But it's saying here we have these two curves, y equals x squared. It's horrible. Y equals x squared and y equals root x. So this is what we had on the screen before. In the first quadrant, meaning here, I mean like here. So this is the region we're interested in. I mentioned that because the in theory the curves could intersect like over here or something. They don't in this case, but yeah. So here's our region. So solid with base, the region bounded by. So this is the region. That's the base of the solid in the sense of the animation we saw before, where I have like my half a potato, and the part that's touching the table is this shaded region. Okay. The cross sections are semicircles. So again, with all these problems, I'm going to draw like a single vertical segment just to help you think about it. So here's a vertical segment. That's supposed to be the base of one of my semicircles. So what I like to do is sort of label this. I'm going to call it D for diameter. So here's my line. I'm going to call this D for diameter. And then I'm going to draw a separate diagram, which is my cross section from the side. Here's my semicircle, and I'm going to also label this D. Right, so the D on the left and the D on the right are talking about the same thing, right? I'm imagining this semicircle glued to the page, where this bottom part is this part right here. And that's what we saw in the animation. Okay, so all I really need to do is find the area of this. And I want to be it as a function of x. terms of x. So it's a semicircle. So we already know that the area of a semicircle is going to be, pi r squared over 2, because the area of a circle divided by 2. So I'm going to need this area. But what is r? Well, r is here, right? It's half of the diameter. It's the radius of my semicircle. So since I already used this letter d, I can say r is half of d over 2 squared. So, this will be the area. So I'm pretty good as long as I can figure out how the d is connected to x. I already said this out loud earlier, but we can look back at the picture here. D is the length of this line segment, which is just this top function here minus the bottom function here. So D is in fact the top function, which is square root of x, minus the bottom function, x squared. Right? If I had drawn a different line, I still could have called it D, and so I guess the first one is D at this x value, and the second one is D at this x value. But it's a function. It can have different lengths depending on what x is. So this is the hardest part, is you have to look at the graph, identify the geometric line segment or whatever it is on the graph, how it's connected to the geometric part of your cross section, usually by a little diagram like this. And then I want to write down the area of my cross section in terms of x. And so I have to think of this d or whatever it is in terms of x. Very typically it's going to be something like this. D is going to be a function minus the other function, and then we do some area. By the way, if I had said that the cross sections were squares or something, I'd have the, if it was squares instead, I'd have the same thing. I'd have d squared instead, because that's the area of my square. And then I'd have to plug in the thing that I just found for d and squared instead. So you could do that problem too. It's a different problem. Let's go ahead and finish this. So I'm going to just leave everything for a second to just show how we're replacing d. So leave everything else, right? Except d is actually square root of x minus x squared. So you kind of write that in for d. Yeah, so that's the first hard part, maybe, is writing down the geometry, connecting the formulas to your graph. You also have to be able to kind of do the algebra and simplify a bit, right? This fraction thing looks kind of gross, but it's not too bad if we just do it piece by piece, right? So let's just keep the pi over 2, and in fact, you can like slide this 2 out in front. That's totally a good way to do it. And then I'm just going to have this fraction here. When I square a fraction, that's the same as squaring the top and squaring the bottom. So I keep the top, square it, and have the bottom also get squared. So let's just keep going. I have 2 squared on the bottom, which is 4. It's on the bottom, so I can bring that 4 in to be multiplied on the 2. And then this is still here. And now we have to basically FOIL this part here. So let's do that. So I'll do square root of x squared. So that's x minus x squared times root x minus x squared times root x, and then plus x squared times x squared. And we can combine these, right? This is 2 copies of x squared times, sorry, this should be root x, I'm sorry. 2 copies of x squared root x. And a really good thing to do here is to combine the exponents, right? What's x squared root x? Root x is actually x to the 1/2. That's one of our exponent rules. And we have a shortcut that whenever I have x to the something times x to the something, like x squared times x cubed is how much x do I have? X xxx, 5 of them, right? So the shortcut here is you can kind of add the 2 and the 3. So same thing here, I can add the 2 and the 1/2, and I'm going to get, whatever 2 plus 1/2 is sitting right there. Now we should be able to do that fraction math. 2 is 4/2, so plus 1 is 5/2. So I can turn x squared times root x into x squared, or x to the 5/2. Okay, so coming back here, we had 2 copies of this x squared root x, so it's 2 copies of x to the 5/2. Remember, we're going to do an integral in a minute is the plan, so I want that to be like a nice exponent form, so I can do my power rule. Okay, great. So that's the area of, it's kind of complicated looking in this case, but that's the area as a function of x. If I want the total volume of my solid, all I have to do is integrate my area. I'm adding up all my little areas from the beginning to the end. So from A to B. Again, I have to figure out what A and B are. It's going to be these 2 intersection points for these 2 functions. So I want to solve square root of x equals x squared. I want to solve that for x. Cool. Something you can do here is square both sides. X equals x to the 4. It's just annoying to deal with a square root, so I might as well get rid of it by squaring both sides. Whenever you're dealing with polynomials, it's a good idea to subtract everything to one side. And then I have common stuff in between these 2 terms. They both have an x in common, so it's good to pull the x out, and you almost always want to do that. And now I'm super happy because I have something times something equals 0. That means either the first part is 0, x equals 0, or the second part is 0. And this one's going to give me x equals 1. So our 2 bounds are going to be 0 and 1, so the 0 makes sense, and then it turns out this is 1. So we're going to get from 0 to 1. And we have our function. And this is an integral that you can do. It's actually pretty straightforward because you just power rule, right? I can power rule each of these parts, and it'll be fine. Let's go ahead and do it, just so if you want to try this on your own, you can check your answer. So feel free to skip ahead if you want to just see the next stuff, but I'm going to finish this integral here. You can pull the pi over 8 out, and then let's just power rule everything. X squared over 2 minus 2x. So I have to plus 1 this, right? So I have to do 5/2 plus 1. 1 is really 2/2, so that's 7/2. And then I divide by my new exponent, which is 7/2. Now I have x to the 5 over 5. And all this, I'm going to plug in 1 and then 0. This is the plan. Now, the reason this is not too bad to do by hand is because I'm plugging in 1 and 0, right? Wherever I plug a 1 in, like the x to the whatever, is just going to become 1. And wherever I plug in 0, it's going to be 0. So here I'm going to get like 1 over 2 minus 2 times 1 over 7/2 plus 1 to the 5 over 5. And I'm not even going to draw the rest of it, but you could subtract plugging in 0, right? Yeah, etc. That's all going to be 0. So we're done as long as we can combine these fractions properly. Again, you could totally calculate this, but just for fun, let's figure it out. One thing to do right away is this 2 over 7/2 thing. Remember, whenever a fraction on the bottom, right, that's the same as multiplying by that fraction out front. So this is actually 4/7. So we have common, we have 2, 7, and 5 as our denominators. So I think we should multiply by, I think 70 is going to be our common denominator. So for 1/2, I want to make it 35 over 70. For the 4/7, I want to make it 40 over 70. And for the 1/5, I want to make it 14 over 70. Right, 7 times 2. Yeah. Right, you can check. 5 times 14 is 50 plus 20, that's 70, so that works. So you can combine the fractions and we'll get a number. Let's just see. So this will be -5 plus 14 all over 70. 14 minus 5 is 9. So it'll be pi times 9 over 8 times 70. And yeah, that is a number. Nothing in common here, so that's the best you're going to get unless you do decimals. Okay. So, yeah, some weird number, but that's the area of our shape. Okay, so these are a little bit tricky because you have to do these cross section things. Cool. On the next problem, it's actually going to be the exact same region, so I'm going to kind of go faster, but the difference is we're going to do square cross sections. So we'll just see like what happens when we do that as well. I basically mentioned it already, but there's a lot we can shortcut, right? We have, so I'm going to draw that better. We have this vertical slice, which I'm going to call D. Now my little diagram on the side, I have a square, right, with the sides D. So the area of that square is going to be D squared. D is the same. D is still, as a function of x, the top function minus the bottom function. And so the area of my square is going to be, whatever that is squared. And to get the volume, we already figured out it's 0 to 1. That's the same thing. And just instead of having the pi r squared over 2 thing, we're just going to have the area of the square thing right here. And that's an integral that you can do. If you multiply this out, it's the same thing we got before, and then you'll plug some numbers in. So I just want to show you how the setup changes just a little bit if you have square cross sections. Cool. Okay, and then for this last example, again, same region, but equilateral triangle cross sections. So, again, same picture. I got my slice, I got my D. D is the same, it's still root x minus x squared. And then the only thing now is I have to think about, okay, what's the area of a triangle? You might know that the area of a triangle is 1/2 base times height, where that's the base, and then the height is like this number. In this case, we have an equilateral triangle, which tells us that all 3 of the sides are the same number. So if the base here is some number b, this is also b, and this is also b. It's because it's equilateral. So, this actually gives me enough information to solve for h. So maybe pause and think about that if you want. It's a good little geometry thing to try. But I will just talk about it. Okay, so to find this volume, the trick basically is, or this area, the trick basically is to look at just this 1/2 of it, where this is h, this is b, and then what's this bottom part? Well, it's going to be half of b. So, like, I have to maybe argue or convince myself that this vertical line that I draw really does cut the bottom length in half. I mean, it's pretty plausible because it's equilateral, but you have to think a little bit about it, right? Like, if I had a not equilateral triangle, then, like, there's different angles that you could sort of pick here, and they wouldn't all, like, cut this in half or anything. So you have to know a little bit about what's going on there. But if you believe that this is really b over 2 on the bottom, which I think is
pretty reasonable. You just say that like what h is going to be the bisector of that angle. Anyway, this side length is b over 2, and now, because it's a right triangle, I guess that's the thing. You have to say that putting a right triangle here is the thing that will make h cut this in half. Okay, so because it's a right triangle, just take it for granted if you're not sure about that. We can do Pythagoras. So I can do b over 2 squared plus h squared is b squared. Right? This side plus this side is that side. This is actually super nice because I want this in terms of just in terms of b. So as long as I can get h in terms of b, then I can plug it into that equation. So let's just simplify this. B squared over 4 plus h squared is b squared. Oh, I can subtract. Nice, right? H squared is b squared minus b squared over 4. And then I have 1 of a thing minus a quarter of a thing. So I have 3/4 of a thing. And if I want to solve for h, I should probably square root, right? H is going to be square root of 3/4 b squared, which is, again, when you square root, it can go on, if I square root a product, it's the same as square root of each of the factors. Square root of 3/4 times square root of b squared. And then when I square root this fraction, it's the same as square root of the top over square root of the bottom, which is 2. And then this will be b. So it turns out, if you have an equilateral triangle, the height is this number, root 3 over 2 times b. And so for my area formula, I can come back here and say, okay, 1/2 times the base times the height is this number I just found. And if I simplify a bit, I'm going to get root 3 over 4 b squared. So that's the area of an equilateral triangle in terms of the base length. Now, you don't have to do this geometry problem in the middle of your calculus homework. I just wanted to include it sort of for fun. You could always look up what's the area formula for an equilateral triangle if you weren't sure. That would be fine. But you know, you could do this. It's not too bad. You just have to be a little determined to see it to the end, right? Okay, so back over in our calculus problem, I want the area of this equilateral triangle. The base I'm calling d. So the area is going to be this thing that I just found out, but I'm going to put a d here instead. The d is the name of my side length, and in this case, d is this thing, root x minus x squared. So we'd plug that in. And our integral, same thing, we just have a different integrand. And again, that's an integral you can do. Cool. Okay, so that's volumes by slicing. So that's very specifically like doing this GeoGebra picture where I have many, many slices that are making up my shape. Another really common thing we're going to do is volumes of solids of revolution. So these are a little bit harder to picture, but the idea is I'm going to take a region, a 2D thing, and I'm going to swivel it around one of the axes, and that's going to generate like a 3D shape. So for example, let's take the graph of y equals root x. Let's just say we're going up to like 1 here. So this, I have a region, 2D region, and then I'm going to rotate this around the x-axis, which I'll draw with an arrow like this. And as it rotates, it's like scooping out a 3D volume. In the end, for this shape, it's going to be sort of like a bullet sort of shape. I'll do my best to draw a picture. It'll be something like this, a little pointier at the tip maybe. Right. And maybe if I want to draw some something like that, but all filled in inside. Yeah, so if you've ever used like a potter's wheel or a lathe or something like that, you may be familiar with this idea. I have like this 3D thing which is rotationally symmetric. It's like made from spinning, and if you adjust one part of it, then like it cuts out a whole circle of that adjustment, right? Like if I went in and changed, right? If this was like a potter's wheel or something, I could push my finger right here, and it'd be like indenting that original function that I started with, and then when I spin it, it would change the overall shape of my thing. Maybe, something like that. I don't know. So you can look up some pictures online, maybe, of solids of revolution. There's lots of different ways to think about it.
One thing to keep clear is what axis you're rotating around. So on these problems, for the moment, we're going to rotate around the x-axis, which means what we did. But it's also possible to rotate around the y-axis. Let's say we had our same shape. But if we rotate around the y-axis, that means I'm taking this thing and flipping it around the y-axis instead. So now my lathe thing is going here. And if we rotate this, I bet it'll make a shape sort of like this. That's like this kind of outside is tracing it. But then as it goes in, it's getting skinnier as it goes in, right? So maybe this sort of like crater-ish sort of shape like that. Not a great artist, but something like that. So like it's totally different whether you rotate around the x-axis or the y-axis. We're going to be able to break up the shape into some sort of smaller shapes in a way that'll be useful. It'll let us do an integral. So if we look at our shape up here, we're rotating around the x-axis. So what I want to think about is that if I look at like my bullet here, I could cut it into these vertical slices, much like on the previous problems, and each of these vertical slices is like a disc, right? Like a circle that's filled in. I have another one here. I have another one maybe out at the front. And I'm going to get these discs. So I imagine these discs as like strung along the axis, right? Here's the x-axis. Here's disc. Here's one of the discs. Here's like another disc. Here's another disc. Like threading a string through each of the centers of them. So, right, x is going to move like from the beginning to the end, right? As it moves, it's going to grab the area of the circle at each of these x values. So area of circle at each of these x values. And I'm going to add all of those up at all my x values between a and b. Very similar to the previous volumes by slicing. It's just that in this case, because it's a rotated solid, the solid that came from rotating a region, I'm going to believe that each of these cross sections are circles. Well, last section I mentioned, like you might have a random volume, and if you can like guess or show that the cross sections happen to be squares, then you could do the volume by slicing method from last time. But here, this gives you a nice way to sort of generate shapes which you know for a fact the cross sections are circles. So if I take any region and rotate it, I'm going to get circular or slightly modified, we'll see in a minute, basically circular cross sections. And I know areas of circles. I can do my integral. So maybe just to draw a little bit more, a good way to think about it is kind of grab some specific x values and think of the circles that are sitting there. So like at this one x value, I have a circle with that radius, and then at another x value, I have a circle with that radius, and at another x value, I have a circle with that radius. So I have all these circles, and they are filling out that total volume, is the idea. It's good to focus on these radiuses that I was drawing, right? That's like drawing this important vertical line segment, kind of like we did in the last problem, right? This vertical line segment, sorry, I shouldn't go that far, is all we need in terms of data, because that's going to be the radius of my individual circle. We'll call that the radius. It's sitting at a certain x value, and that x value is somewhere in between my beginning and my end, right? I said we were going from 0 to 1, so let's put a 1 here. Okay, so I want to find a function for my radius as a function of x, and I'm going to use that to get an area of my circle as a function of x. Area of circle. The radius is just this geometric length. So just like before with the area between curves stuff we were doing, it can be the top function minus the bottom function. Top function here is just root x, and the bottom function is, y equals 0 on the bottom. So I can just write root x. My cross sections are circles with radius root x. So the area of a circle is pi r squared. Here our r is root x. So root x squared. And we just simplify to pi x. So this is the area of one of my circles, and now we just integrate. So I go 0 to 1, pi x. That's it. That's an integral that you can do. It'll be pi times x squared over 2, 1 to 0. You're going to get pi over 2. You can double check. So yeah, it's pretty straightforward as long as you recognize that it's a rotated thing. My cross sections are circles, and I can connect the radius of the circles to the graph. So you can do all sorts of problems like this. You could have any sort of weird function, but as long as we're rotating around the x-axis, right, and I get these circular cross sections, then I can find the volume of any region like that. So that's pretty cool. So this whole method is called the disk method. So these things, they're calling them disks. I was calling them circles, sort of the same thing. We're breaking it up as a bunch of circles, disks. Let's just do another example really quick. So R is the region bounded by this random curve and the x-axis. We're going to rotate the region around the x-axis. What's my region? Well, I need the graph. So this is kind of hard to graph by hand. So if you plug that into a graphing calculator, you will see that you get something that looks sort of like this. And now I want to think about rotating this around the axis, my region, right? So I'm going to get a bunch of circles. One sort of example circle is going to have this line segment as its radius, and it's going to be sort of swung around this way, right? What's my radius? It's the function itself, right? The top function, y equals, minus the bottom function, y equals 0. So the radius is just the function itself. And then the area is going to be, pi r squared, where you're using this as your radius. So we'll integrate pi times our function squared. That's pretty much it, as long as we plug the bounds in. It looks like it's 0 and something. Let's just check. I want to see where my function, where it intersects the y-axis, right? Where does it happen that the output is 0? So I set it equal to 0, and then I just solve. This is already in nice factored form, which is great. remember we can have this logic where if I have something times something is 0, then one of the pieces has to be 0. So here right, the three possibilities are an eighth equals 0, x squared equals 0, or root 2 minus x equals 0. The fact that I have something times something times something equals 0 means that one of these, at least one of these things has to be true. Now it's a little silly. I didn't have to write this eighth thing. We know that's not true. Another way to say that would be I could multiply by 8 first, and the 0 will kill it. And then we have the equation without the 8. Regardless, this one gives us that x has to be 0. And this one, well, probably x equals 2, right? Because that's something that will make this 0, just by looking at it. But we can also algebra. If I square both sides, I get that, and then I can solve x equals 2. Nice. Okay, great. So we know our bounds are 0 and 2, and that makes sense. Here's 2, there's 0, 0, 2. And this will be an integral that we can do. Just to show off a little algebra here, the squared can go on to the 8. It can go on to the x squared, and it can go on to the 2 minus x root. All right? And then I could multiply the x to the 4 through. And now that's an integral that you can do with power rule. So I'll let you finish that if you're interested. But yeah, that's the setup for this one. Okay, so yeah, cross sections, circles, you can do it. One thing I want to emphasize, just because this could be confusing. In this problem, I said I'm going to take this region, and then I'm going to rotate it around the axis. That gives me like a teardrop-shaped region whose cross sections are circles. That's very different than if I had said, here's my region, now I'm going to make a volume whose cross sections are circles. Right? That sounds very similar. On the left, we have a region who, when I rotate the region, I get a volume whose cross sections are circles. But on the right, I'm saying I have a volume which has a base region that's flat on the ground, and its cross sections, sorry, not flat on the ground. I have a base region whose cross sections are circles. Right over here, if I have circle cross sections, I end up making like this teardrop sort of shape when I rotate it. Over on the right, if I have this region with circle cross sections, where the circle is the base, I didn't say anything about rotating. Right on the left, I rotated it, and that's where the circles came from. On the right, if I just said it's a volume with this base whose cross sections are circles, that would mean something like each of these horizontal slices is like the diameter of a circle. So I'd have a circle here, and a circle here, and a circle here, and a circle here, and a circle here. And those, like, all together would make up the total volume. That's very different than on the left, where I have circles whose radiuses are given by the function value. And notice on the left, these circles are all like sort of centered around that same central axis, right? We're rotating around that same axis. On the right, the circles have like varying like centers and stuff, and it's kind of weird. The 3D shape would be very different. So that's easy to kind of confuse those two. If the circles are coming from a rotation around an axis, it'll look like this. But if we were doing like this kind of thing, where you happen to have circles, now that's semicircles, so that's different. But if you imagine these are the bases of circles instead, I'd have like circles sitting at each of these segments. So that can be a little tricky. Okay, so we've talked about this is the disk method. We're also going to talk about the washer method. So basically, sometimes we have a gap between our shapes. So let's look at this region. So this is going to be the region bounded by the two curves, same ones we've been seeing a lot. Here's root x, and here's x squared. Now we're going to rotate this region around the x-axis. Let's try to picture what that shape would look like. There are points on sort of the inner edge, and there's like points on the outer edge. When I rotate this point on the inner edge around, what's going to happen is it's going to rotate and kind of trace out a circle like that. The point on the outer edge is also going to rotate and trace out a circle. So instead of getting like a circle cross section, I'm going to get like this washer shaped cross section. So that's where this name comes from. You might also hear the word annulus. So it's a shape that looks like a circle where I cut an inner circle out of it. Yeah, and so what's different here is that I have, unlike before where I just had one radius, here I'm going to have like an inner radius and an outer radius for each x value. Right, here's a vertical x value segment. It's going to give me an inner radius and an outer radius. So a little bit harder to draw. If I tried to draw the actual 3D version of that, sort of on the outside, we'd still have that sort of bullet shape from before, I think. But we'd have this like hollowed out inside piece, right? Which would, it's a little hard to draw, but maybe something like, because like it comes to a tip here, so on the inside, and then it comes up to like that, I think. So I have like this hollowed out, this sort of hollowed out thing going on. It's a little bit hard to draw. Something like that. Right. You can really think of it as taking the original outside thing, like the original bullet shape, and cutting out something on the inside. Sorry. Cutting out something on the inside. Just like on the individual disk level, I took this larger disk and I cut out the smaller disk. How would I find the area of one of these washers? It's exactly what we just said. It's a big disk minus a small disk. Like, you should think of this as equals taking the area of the big disk minus the area of the small disk. That's how I get this area of my washer shape. What's the area of a big disk? It's pi big R squared, right? If I just label this big R. What's the area of a little disk? Pi times little r squared, if I label this little r. And then I could subtract them. So this is going to be the area of a washer. So that's exactly the thing we're going to integrate. Pi r squared, where r is the bigger radius, minus pi r squared, where r is the smaller radius. We can extract what the bigger and smaller radius are just by looking at the graph. So if I draw it a little more clean here, again, draw one slice, line segment to help you. It's just a representative line segment. It's like one of these. You can imagine there's a washer attached to it. Where's the big radius? It's here, right? Where's the little radius? It's here. So these are connected to the equations of the graph. We have to think about it a little bit. I bet the big radius is just this functions, right? Like the distance from 0 up to that function, from the axis up to that function, is just the thing itself. And then what's my little radius? It's the distance from 0 up to the smaller function. So that's just x squared like that. Cool. So that's my big radius and that's my small radius. So I'm just going to integrate
pi times the big radius squared minus pi times the little radius squared, which is going to be pi times root x squared minus pi times little radius is x squared. It's really common. You'll see people pull the pi out because there's a pi in each part, right? So I can pull pi out, and if I do these powers, I'm going to get x minus x to the 4. Our bounds here are going to be 0 and 1. You can check that with some algebra. Just set these equal, right? Okay, so that's an integral that you can do. So again, it's not really that crazy. It's just kind of hard to visualize conceptually what's happening, but as long as that makes sense, you just have to do big radius squared minus the smaller radius squared all times pi, and that's going to be the volume of your thing after you integrate. Yeah, so this is kind of one of our main methods. So doing the discs and the washers is just a little extension of it, is really like a level up to finding the volumes of all sorts of interesting looking shapes. Cool. So I think I have one more example right here. So let's have R be the region bounded by these curves and find the solid generated. So let's take a look. So we're going to have, just going to draw this picture. Y is 1 plus root x. So it'll look like root x, but shifted up by 1. So there's a 1 right there. Y equals 1, so that's going to look like this. And y equals 4. So let's put a 4 here and look like this. This keeps going. Find the volume of solid generated. R is rounded by, revolved around the x-axis. So we have to think about what is our region here. 1 plus root x, y equals 1, and y equals 4. So I think this is a typo. See, this doesn't really make sense as it is. The region, there's no region that these three things bound. I think I meant to say x equals 1 right here. That would make more sense. Let's just roll with that. So the reason x equals 1 makes sense is if I put a 1 here, x equals 1 makes this vertical line. And now this region here is totally a region that we could rotate around the x-axis. Again, you don't really have to picture it. That's kind of just like a bonus if you can picture it. But I think the picture here would be something like we'd have that inner radius at the end, and it would sort of like scoop up. Yeah, something like that maybe. A little hard to draw. So yeah, so we have our various washers, right? Let's just draw a single representative line for a washer, that one. And again, we have our big radius, which goes to there, and our small radius, which goes to there. What's my big radius? Well, it's always 4, right? You could think it's the function y equals 4, but it's also like it's always 4, right? As I go from 1 up to whatever this point is, which we'll figure out in a minute, call it b. As I go from there to there, the outer radius is always 4. What's the inner radius? Well, it's just this distance from 0 up to our function, so it's our function, the bottom one. Cool. So now we just got to integrate pi times big radius squared, so that's 4 squared, minus the small radius squared. That's that. And we got to integrate from 1 up to whatever b is. Cool. We can solve for that. We just got to set the two equations equal to each other. Right, 4 equals 1 plus root x. So 3 equals root x. So x has to be 9. So b turns out to be 9. So we'll integrate from 1 to 9, this thing. And again, that's an integral that you can do.
Okay, cool. So thanks for listening. The next lecture we'll talk about volumes of solids of revolution, which is just another method. With shells, which is another method for solids revolution. But yeah, see you next time, and let me know if you have questions.